Hi everyone, I'm Deepak, and just one disclaimer in the beginning that I'm not a cognitive scientist. I'm a machine learning person, and I do robotics and vision. So many things that I might say in the talk might be incorrect. Please do correct me if you think I'm saying something blatantly incorrect. Uh, I am sorry about that in the beginning. Okay, so let me begin. So the question, what I'm really interested in is that how do we build intelligent machines, right? And specifically robots. Well, this is a cartoon picture of a robot. In reality, the robot might look something like this. And the usual way that we train these robots is either we try to imitate humans and train them via multiple tasks by showing expert demonstration, rewards, labels, supervision, and basically trying to make them mimic human intelligence in some way. But in this case, what we have found that if you train robot for one task, it's very hard to generalize beyond what you are trained for. So as argued by Turing over 60 years ago, and many people in the talk today, we should perhaps train these robots like a baby. And what I mean by that is that train these robots the way babies learn, that is without any goal, completely self-supervised, driven by curiosity and things like that. In fact, I have spent much of my PhD in trying to build algorithms that can scale, that are inspired by curiosity or learning in humans, and can scale them to several scenarios in simulation and these robots. And the results I'm showing here are all the results which are where the agents are training only via curiosity and no reward at all. And we can show very good performance across large variety of benchmark and almost match the performance of Oracle, which are trained with reward from scratch. And so although this line of curiosity-driven learning would have fit the theme of the theme of the workshop really well, but I thought since the workshop is about origins of common sense, I thought I'd talk about something very different than what I've been working on. So today's talk is not about curiosity-driven learning, and I'll talk about can we thinking about the problem of embodied intelligence in a more fundamental manner. So if you learn from babies or humans, adults, there is always this question of nature versus nurture, as in how much do we build in and how much is already there to begin with. And as a psychologist, one might be interested in the timeline of humans from babies to adults. But as I said, I'm not a psychologist, I'm a computer scientist, so I work with computers. So the hard work is not done by me, it's done by the computers. So I can really take a bigger picture and look and go way back, not just to babies and where humans are born, but way back in the timeline, and really start simple, because just to find out where do these complex things emerge, because this notion of nature versus nurture is a question about human timeline. But if you look at this giant time scale, everything basically evolved from calcium, magnesium ions combined with each other. So this, what we call this prior knowledge must have evolved somewhere, must have emerged somewhere in this long timeline. Okay, so but what is even before all this? What was even there? Well, long before even brains evolved, there is this intelligence in terms of cells. So like this, you can call this a so-called Big Bang of evolution. Like one was the formation of cell itself, but that we don't know about much. But this phenomena when cells combine to become multicellular. And this is one stage where already we start to see some signs of intelligent life way back before even the brains have come to the picture. And this kind of intelligence, I would say, is a collective and distributed intelligence. In fact, there are still some species around which kind of demonstrate this intelligence in terms of which is distributed throughout their body. So for instance, this is a great talk by Michael Levin in NeurIP's keynote a couple of years back, where he shows examples of this flatform where each cell in the flatform basically has the structure of the whole body, including the brain. And you can cut these flatforms from tail, and you can change some electrical signals, and the tail cells start to grow heads on the tail side. So as you are seeing over here, these are two-headed flatform, which kind of suggests that the blueprint of the whole body is there, not just in the brain, but throughout the structure of the body. And in fact, these are slime molds, which are other examples where the intelligence is distributed throughout the throughout the body of the agent and not just the brain. And one of my favorite examples are these Armenian ants, which show a very intelligent behavior in as a collection, and like they can build these bridges, etc., etc. And they can do lots of complex things. And this is not driven by one single entity. It's driven by a behavior that is coordinated across the body of the agent. In fact, for ants, sometimes people also call that ant itself is nothing, but ant colony by itself is a singular and it's not plural because it is so tied to each other. But how does this can help embodied robots or my goal of building better robots? Well, the part which I am most inspired by in this single cell to multi-cell agents is that notion of going from competition to collaboration. Like this was the time back in the day in evolution when things went from always competing to combining. And when these cells combine, they share the objective and they turn into a new agent which has, which it's not a two-cell agent, it's a new agent which has two cells, okay? So this kind of compositionality has been really useful in language. For instance, you might have seen this work on modular networks and vision. In fact, the compositionality that people have explored in the vision context, I would say is still very similar to it is applied on language in terms of objects, background, and reasoning out entities. But this is not what I'm talking about today. What I'm talking about is implementing this compositionality at the level of hardware itself. So it's not about you have a body and you're trying to figure out where the objects are or where the entities are. This is all about how can we enforce this compositionality and how do we discover it at the first place through the body of the agent. Now, we were kind of overwhelmed by this problem statement. So we started really simple in the beginning. So to study this problem simply, before I go to real robots, let me first show some examples in the context of simulation and very, very simple agents. So we tried to design these robots, which are basically a cylinder and a motor. So it's a physical system. So it's a physics engine on the left. It's not just a magical simulation. It's a proper physics engine, which is Unity. And we have a proper robot, which is motor and a limb. But these agents are really stupid in the sense that they cannot do much. All they can do is rotate and apply 3 torque. But we give them the ability to combine with each other via magnetic joint. So they can apply magnetic force and become more complex. And when they combine, their rewards get shared and they act like a single agent, okay? So really the analogy over here is that these agents are kind of like cells which only observe local information, no global idea of anything. They only observe their nearby things and they can output torque. They can choose to combine or choose to detach, okay? And what's the approach here? I'll go into the details a bit later, but let me first give you the approach. The approach here is to basically leverage this notion of compositionality at the level of the body of the agent. What I mean by that is that you have a policy, not for the full robot, which is the current way people approach these problems, but have this policy for each motor of the robot. So there is no centralized brain or anything in this case. Everything is fully decentralized. And our hope is that can we show this global coordination emerging from nothing, from no coordination, okay? So this kind of approach, what we, like, before I go into the details, let me show results first. And in this case, let's consider 2 tasks. We give this robots 2 tasks of standing up on the top and locomotion on the bottom. And our goal is, since these agents discovered their own structure through all this combination and fighting and collaboration, our hope is that these robots will probably be very general purpose. So at test time, we'll take these robots and without any further training, we'll test them in several new settings without any training. And we'll see how well they do. And in this case, let's see an example of like the standing up task, the first one. And before I go show these results, let me show why this task is even hard for vanilla reinforcement learning for robot control methods, what people usually do. So if you're trying to make this one robot stand up, it's easy. You can make 2 of them stand up. So note the task here is like balancing a bottle in your hand on top of each other. So if you keep stacking them one over each other, and it's a continuous control task, if you have lots of things to manage in your hand, the problem becomes very hard in the sense that this works for 1, 2, 3 like agents, but it fails to scale to like 6 agents on top of each other because your action space is increasing linearly. But instead of that, what we do is we allow these agents to self-assemble and become complex on their own. So for instance, in the beginning of training, these agents are completely stupid. They don't do anything. They just roll around and are trying to learn how to combine as well as learn their software to control itself. After training, they start to make, so the goal over here is to maximize the height. So they are making a tower after being trained for some time. And note that now they can control 6 limbs, which they could not train earlier if you train from scratch from a full body, right? So what I'm just describing here is basically like curriculum learning, but it's happening in hardware. It's not just software. So our goal is that since this is a curriculum learning, it should generalize better. So I'll test the same agent on a number of scenarios. So at test time, let me replace the number of limbs and increase them by 2. So now it has 6 to 12 limbs, and this agent can still stand up and make a tower over here. Note, this is a real physics simulation, so they have continuous control. So making a tower of 12 limbs is very hard. So it does not generalize perfectly. But if you decrease the number of limbs, it makes a perfect tower. You can also add forces on these agents, and these agents can still adjust their limbs at test time without any training to balance themselves. Okay, let's see more. The task of locomotion. Now, in this case, these agents that goes to move to the right. So they make this weird shape to move to the right, and they can make some progress. And note the surface over here is bumpy surface. So they have to slightly work hard to move to the right. Now, again, test time, no new training, the same old agent, and I increase the number of limbs twice. And it can still move forward and do interesting things. But I can also change the terrain from the previous one to this new terrain, and the same robot without any training can still generalize. This is a kind of interesting generalization that is happening over here without any new training. And our hypothesis is that since these agents are fully modular and fully compositional, so a bumpy surface for a small agent is kind of similar to a giant hill for a big agent. Now these agents are fully modular, so they can also drop limbs in the gaps, and they can still keep moving, because they're fully regenerative in some ways. Okay, so this was our first attempt in trying to take inspiration from these biological creatures which have intelligence distributed around the body. And what we found that encoding the similar idea actually leads to very good generalization. But what about normal robots? These were still very weird robots which are combining with each other. And can we apply this idea to general useful, like everyday robots? And in fact, even in everyday robots, the problem is still very hard because we can do all these fancy tricks as we see on the left side, but these robots miserably fail to generalize when tried on very simple new tasks, which someone might say should be in common sense. And they fail catastrophically in many scenarios. And in fact, the problem does not stop there. Like every robot is different, and it's very different. It's very hard to generalize anything from one robot to other robot or come up with a new policy. For example, this robot is NASA's dexterous manipulator. Nobody even has this robot. And how can you generalize to something like this without training at test time or start with some reasonable priors for these robots? And in fact, one could use reinforcement learning kind of things, but it's already very hard to train these reinforcement learning systems on the training agent. Forget about generalization to new agents with slightly different change in shape. Like if I just remove the feet, it completely breaks apart. And people have tried to address this problem in the past, but the variations they consider in the robots are really not that diverse. On the left, all these arms have different shapes slightly, like they have different degrees of freedom. On the right, there is this caterpillar with different number of legs, but people usually assume that the topology of the robot remains the same. While what we are interested in is really learning a general purpose robotic system, which can be shared across several robots and generalized to new robots at test time. So what I am going to talk about now is like, how can we use similar idea of distributed intelligent behavior to train not just 1, 2, or 3 robots, but a large number of robots with a single policy. So single controller that works across all these agents. And at test time, I'll show results on new agents, which the agent has never been trained on. So it's a challenging task, you can imagine. First obvious reason is that every robot is very different. They have different number of limbs, different input. How can I train a single thing for everything? The deep networks need same output and same input, right? Okay, that's one problem. But the bigger challenge is that every robot needs to show a different behavior. So it's like that ant colony. They have to make a bridge. They have to make something else. And how do I represent everything from a single policy? So that's the challenging part. So it's a bit too challenging to begin with. So we thought about it and why should it be possible? And in fact, there is a very good reason, again, this motivation from biology. So this slide is from Robert Full. So what they show over here is that very different species like this ant, crab, dogs, humans, they are all very different, but when they walk, they apply similar forces on the ground. And so they share some collective intelligence, even though these are very different species. Other example is of these precocial animals, which is super precocial animals, like which basically start to show these intelligent behaviors, not maybe common sense, but intelligent behaviors right after birth, unlike human babies, which take months to show any signs of walking or any meaningful behavior. And this kind of is one maybe small evidence that maybe it's possible to pre-train a policy which can then can be confined into a very small genetic bottleneck such that it can just reproduce after birth and doesn't even need learning. And so we try to address this problem over here and try to apply the same idea across practical robots, which do not need to change their shape to work. Okay, so how do we do this kind of thing? Again, the key idea I mentioned earlier, that we share the policy, but it's not as straightforward as I explained earlier. Let me first explain how do we build this system. So for all these agents, we take any of these agents and we train a single policy for each of the limb. And this policy is shared across all of them, not just for one agent, but across all the limbs of all the agent. Okay. Now, does it just work like that? No, because there is no brain, right? This is in some ways there is no global coordination. There is no one over here that can decide if the same hand has the same policy as the leg, as the brain, and they don't know what to do unless you give them some context. So to give them some context, what we notice over here, that we are applying same policy at the torso, at the leg, at the feet, as well as at the head. Right now, our policy cannot, our usual networks can be applied like this, because networks has different input and output shapes. So I cannot put one network on top of each other or at the bottom of each other, right? They are not like Lego blocks. But what we really want is that networks that can act as Lego blocks, in the sense that I should be able to put a Lego block on top of each other as well as at the bottom, because they have a hook which allows them to attach. These networks have different input and output shape. So what we do is we create a hook, and this hook is just a vector, which is a learned vector, but it lives in a same dimension. Now, if I have a robot over here, I just copy the policy 3 times, and to allow them to talk to each other, I just allow them to pass messages from one limb to other limb, and they can talk to each other. Okay. Now, once I have trained the robot at training time, let's say this is my robot with corresponding policy. At test time, there's a new robot. I can just cut the policy from here and paste at a new location, and it will instantly adapt without having to fine tune. So note, the adaptation is instantaneous over here and no fine tuning going on. Now, how do you allow them to talk to each other? Well, you can either pass messages bottom up or top down, right? Leaves to root and root to leaves. Note that any node can be a root node. I'm not defining a brain has to be a root node or the torso has to be a root node. Any node can be a root node. The graph is completely imaginary. So you can pick any node to be a root node. But if you only pass messages one way, again, the brain kind of thing cannot really emerge with just one way message passing, because you can only represent one behavior. You can either everyone hops or everyone walks. Like in the beginning, everyone hops, like this 2-legged thing also is hopping. And at the end of training, everything walks, but then this does not work because it does not have 2 legs to walk. It needs to hop. So you cannot represent multiple behavior with this. And to resolve this problem, what we propose is topological message passing, that we pass from bottom up to the all the way to the root node, which can be any node that you picked, and then from root all the way to the leaves node. Okay, very simple idea. And while you are coming down, you output actions in the downward path. So you go up, collect messages, and come down, and then you output actions. Now, why do I say there is no master node over here? Because every policy is same. Even the root node, which aggregates the messages from other nodes, is the same policy. But we hope that it will the communication will just emerge between these decentralized modules if you train them together. And in fact, that does happen. Like over here, I'm showing result of a single policy that can make all these robots walk in very different fashion. Like if it has one leg, it hops, otherwise it walks. The same policy applied to these other agents. This one is, you can see that the diversity in behavior, even though the same policy is shared by legs, hands, torso, everything has the same policy. And look at this diversity. Like this one is just doing something very different than other agents because it has a very short back leg. And this is all happening with a single policy. Now, can I generalize again? Yes, because I trained on diverse agents at test time. So these are held out agents, but this is a boring result. Even though I'm not training on them, but they look very similar to the training ones. Can I actually generalize to out of distribution and completely different agents? So what I show over here are very different agents than it was trained on. And if you see, like, it does not show a very excellent walking behavior or running behavior, but it is trying to like stand up and not fall, even though none of these agents were trained on. Like this has very heavy hands, this has multiple legs, this is very different diverse behavior. I can add objects at test time just to annoy them a bit more, and they can still generalize to some extent. Does not excel, but this is again, no training here. This is complete test time, zero shot performance. Sometimes, okay, we went a bit too far and we increased the weight of the limbs a bit too much, and then your motors cannot really control the agent, or we remove the legs altogether and they try to use hands. And these are some of the failure examples. But this last part of the talk is, is this method delivering on the promise of that centralization is emerging and from this decentralized controllers? Because in humans, you can measure it by this biological central pattern generators, and which are shared by many species, not just humans, like crabs, etc., etc. So to find whether similar emergence is happening in this case as well, or any of that indication, what we do is we take the messages of the root node, whichever node we pick the root node, and we observe them. How do they look when we plot them in an episode? So what I'm going to show now is that the variation of message of root node across an episode and its one-dimension projection on the y-axis. Now, in the beginning of training has just begun. It's nothing interesting here. The messages are almost zero, and then they don't show any signs of life. But as you continue the training, these messages start to take some shape. And towards the end of training, we found that on the right, this end of training, within an episode, the root node starts to act like a master. You can say some analogous to central nervous system. It starts to monitor the shape of the body, where these peaks start to correspond to the walking behavior of the agent. Like the down peak asks the agent to make this shape, and note this root node has the same policy at the foot of the agent or the hand. And even then, only with this compositional structure and training, the same policy, if applied to the root node, just behaves differently and starts to show this emergent centralized coordination completely from decentralized policies. But is it applicable to real robots? Like this is still very in the fancy land, right? In fact, I would say modular robots is already there in the real world. But the fact, what is missing in these robots is that they are controlled manually by someone controlling from a corner. While what we are developing is software of these robots simultaneously with the hardware. In fact, we are also attempting in, like for example, one of the robots over here is this heavy robot, which has a similar motor across all joints. And this is one of the ongoing work where we try to make these robots walk. These are not yet decentralized, but they are hierarchically decentralized in some ways. And you can also apply this to walking, and these are very ongoing attempts, and we are still thinking about how to scale them to more complex scenarios. Okay, just to summarize last 10 seconds, in my research, what I'm after is building these embodied robots which are intelligent, I'm focusing on two approaches. One is ontogeny, like how much can I learn during the lifetime of this robot, which is like driven by curiosity. And second is phylogeny, how much can I build in from this global picture of evolutionary picture at a large scale, which is modularity. I didn't talk about curiosity, but feel free to check out my webpage for all the papers and modularity what I talked about today. I would say these are still very super early, like we are barely scratching the surface here, but I think there is a very promising result and still a long way to go. Everything is on my webpage, including code, models, papers. Thank you.